So you've got this tiny chip in your hand, a PIC microcontroller, and it's just brimming with potential. But how do you actually tap into that power? How do you make it do something? Well, that's what we're going to get into right now. We're going to look at the software side of things, from writing that first line of code all the way to zapping it onto the physical chip.
All right, so let's jump right in. What you're looking at here is the starting point for pretty much everything. This is MP Lab, the official integrated development environment for Microchip. You can think of this as your digital workbench. It's the command center, the central hub where you're going to write, test, and ultimately send every single instruction that your microcontroller will ever run.
First up, let's talk about that digital workbench I just mentioned, MP Lab.
Okay, so before we even think about writing code, we've got to know our tools, right? The cool thing about MP Lab is that it's a completely free all-in-one package. It's got everything. You get a text editor for actually writing your code, you get an assembler, which translates what you wrote into something the chip can understand. It even has a simulator, which is awesome for testing your program virtually and catching bugs before they hit the real world. And finally, it's got the programmer part, which lets you download the code to the physical chip. Seriously, it's the whole shebang, all in one spot.
All right, so our workbench is ready to go. Now we got to learn the language, and we're starting with assembly. You can think of assembly as the native tongue of the PIC microcontroller. It's like you're speaking directly to the hardware, no middleman. And that means you get the most precise, absolute control possible.
Okay, let's break down what a single line of assembly actually looks like. First, you might have a label, like start. Just think of it as a bookmark, a name for that specific line of code. Then comes the mnemonic, BTSS in this case. That's the verb, the actual command you're giving. After that, you've got the operands, port D, inres. These are the nouns. They tell the command what to act on. And last but not least, the comment. This part does absolutely nothing for the chip, but trust me, it's super important for us humans to remember what on earth the code is supposed to be doing.
And here's where the magic really happens. The assembler takes our nice human-readable instruction, with its mnemonic and its labels, and it crunches it all down into a single binary number. Yeah, just a string of ones and zeros like you see here. This is what the microcontroller actually understands. It's the rock-bottom fundamental language of the hardware.
You know, good programming isn't just about getting the code to work. It's about making it understandable later. A well-structured program is basically a gift to your future self. It all starts with a header, file name, author, date. Then you have the configurations for your specific chip, where you set up things like the clock speed. After that, you define any constants. Then you write the main program, the core logic. And finally, you can organize reusable chunks of code into things called subroutines. It's all about creating a clean, logical blueprint that you or someone else can actually follow.
So we've talked about instructions that speak directly to the chip. But there's another kind of command you'll be writing, one that doesn't talk to the chip at all. It talks to the assembler software on your computer. And these are called directives.
Okay, let's make this crystal clear, because this is a really important concept. An instruction, that's a command for the hardware, for the chip itself. But a directive, that's a command for the software, for the MP Lab assembler running on your computer. It's basically you giving instructions on how to organize and set up the project. That code is never ever sent to the microcontroller.
So let's look at a few of the most common directives you'll run into. You've got processor, which is pretty straightforward. It tells the assembler exactly which PIC model you're using. Then there's config. This one sets the chip's internal fuses, which are like permanent settings for things like the clock type. Equa is super useful. It lets you give a nice, readable name like run button to a number so your code makes more sense. Include lets you pull in other files like standard definitions. And then there's end. And well, that one's a bit special.
And this really hammers home why end is so important. Look, while all the other directives are about making your code clean and setting things up correctly, end is the only one that is absolutely 100% essential. It's the period at the end of your program. It's you telling the assembler, okay, we're done here. Stop reading.
Okay, so assembly gives you that ultimate down-to-the-metal control, but it is very, very low level. For bigger or more complex projects, a lot of developers switch to a higher-level language. And when it comes to PIC microcontrollers, the most common choice by far is C.
Think of C as being, well, a lot more like English. You write statements that are much easier for a human to read and write. And then a special program, called a compiler, does the heavy lifting. It translates your C code into the exact same kind of assembly instructions we've just been looking at, all behind the scenes. It adds this layer of abstraction, so you're not micromanaging every single bit and register. And man, this can make development go so much faster. But there's always a trade-off, isn't there?
That convenience comes at a cost. When a sample program was created in both languages to do the exact same job, the C version ended up being 40% larger than the hand-coded assembly version. What does that mean for you? It means it takes up more precious memory on the chip and can sometimes run a little bit slower.
So let's put it all side by side. On one hand, you have assembly. It gives you raw speed, super compact code, and total control. It's perfect for those times when every single microsecond and every single byte of memory is critical. On the other hand, you have C. It's all about faster development, code that's way easier to read and maintain, and it's definitely the better choice if your project involves a lot of complex math. Now, here's a piece of advice that applies no matter which language you pick. The best programs don't just happen in the text editor. They start with a solid plan, and especially for assembly, one of the best planning tools you can use is the good old-fashioned flowchart.
And the beautiful thing about flowcharts is how neatly they map to assembly concepts. It's almost a one-to-one translation. See a rectangle? That's just a sequence of instructions. A parallelogram for input or output? That's you reading or writing to a port. That diamond shape for a decision point? That translates directly to a bit test and skip instruction. And even a subroutine has its own symbol that lines up perfectly with the call and return commands. It's literally a visual blueprint for the code you're about to write.
So, at the end of the day, it all comes down to a choice that you, the developer, have to make. Do you need the surgical precision and raw efficiency of assembly? Or do you need the rapid development and readability you get with C? There's no single right answer here. It all depends on the project. The only question is, which tool is right for your next project?